First of all, I want to start off. Javier yesterday pointed out a mistake I made, which was really interesting. And I just wanted to spend a minute on that just to tell people what's going on, because I learned something from this. And it has to do with the following. The group here that's relevant is not actually just the rotations of the sphere, because there's an additional angle, which is the phase. It's the angle that the m hat and n hat vectors form with respect to omega. That introduces an additional angle psi. And as a result, the actual group of relevance is U2. SO3 is roughly equivalent to SU2 up to double covering. These are matrices with determinant 1. These matrices, on the other hand, have a free phase. It's one extra angle. And so it turns out the quantities I was looking at, one should not ask about their behavior under the rotations, but under U2. And if you do that, for example, quantities like m plus in, these transform to m hat plus in hat with an angle psi. And so if you look at quantities, for example, like the average over the sphere of m hat plus in hat, these are not 0 because we haven't averaged over the entire group. The argument that you get 0 only applies if you also average over this angle psi. And so an interesting question is, why is it that, for example, some quantities don't require that average? And a good example is this. If we take m hat plus in hat times m hat b minus in hat, this transforms with an e to the I psi, but this one transforms with an e to the minus I psi. Those cancel, it's psi independent, and so this averaging isn't necessary anymore. And in fact, if you think about it, this is m hat minus n hat, sorry, plus n hat. And if you average that, d omega, you get 2/3 delta AB. And Javier, if you tell me that's wrong, I'll be crushed. And so, in fact, you can form quantities that are independent of this phase psi. Their averages over the two-sphere can be computed by these symmetry arguments. But if you have quantities that contain the psi, then you have to do a little bit more work. So anyway, that's what went wrong yesterday. And as I like to tell people, I think the mistakes you make are some of the most interesting things that you do, because you can learn from them. And so if you make a mistake, don't brush it aside. Actually, explore it. That's how you learn. OK, so just a bit of review from yesterday. We'd written down a formula for the redshift as a function of tau, as a function of time at a pulsar. And it looked like the following. It was the sum over polarizations, an integral over frequencies, an integral over directions. There was the gravitational wave amplitude HA at frequency f in direction omega. Then there was a response function, I'm going to call it FA, that was kind of a geometrical quantity determined by the direction to the pulsar. And finally, there was the difference between the Earth term and the pulsar term, which was 1 minus a phase e to the minus 2 pi I f, the distance to the pulsar, 1 plus omega hat dot p hat. OK, and that's kind of where we had left off. And there was this antenna pattern function here that we were talking about. This dotted white line is the modulus of f. So I'm going to now write the complex version of f. So that's the plus I times the cross, which was 1/2 p hat A, p hat B, dotted into a polarization tensor. This is the complex one in direction omega, divided by 1 plus omega hat dot p hat. So real part of this E plus, imaginary part E cross. So that was describing this white dotted line here. And then this side lobe pattern was formed by the place where this quantity in square brackets goes through its maxima and minima. And I think I was asked the question, who was it who asked me the question about why the lobes aren't evenly spaced? Someone asked me that. It was a good question. And the reason why was because the dot product that appears here, if you think about that dot product, it's the cosine of theta. And so if you want to think about it geometrically, you know, cosine of theta looks like that. If you want to evenly space this argument, the cosine of theta, you know, you find that the values in theta are spaced rather far apart, if that's theta along the axis here, near 0. So that's the reason why these things are sort of farther spaced apart. Okay. Say again?
Is there exponential missing in Z? You have exponential here of 2 pi I f tau.
I think this is right. It's e to the minus 2 pi IFL times 1 plus omega hat dot p hat. Am I missing something there?
I thought apart from this, there was another one. F tau.
Oh, I'm sorry. I've forgotten the exponential. Thank you. Good. Okay. This is the danger of not working from notes. IF tau. Okay, thank you. And by the way, I mean, this should make somebody like Teja, I mean, your heart should bloom at this, because you say, I can read off what the Fourier transform is of Z. If I want to know what Z tilde is, just drop this e to the 2 pi f t and the integral df. So this is a nice expression if you're working in the frequency domain, because you can drop that. Okay, thank you. Any other mistakes of note here? All right. Let me just show a couple of slides here. I think that's all I wanted to say as way of review. Yeah, that's good. That's good enough. Okay. I wanted to show this just for fun. So in principle, in an ideal world, Barak's spherical horse, this would be enough to detect gravitational waves, because you just look at the redshift of a pulsar and see what it does. And for example, if there was no noise, if pulsars were really perfect clocks, we had perfect receivers, lots of data, here's an example of what you might see. So for example, here we are looking at the redshift z as a function of time. This is 25 years on the horizontal axis. Suppose you saw this pattern in the redshift. So redshift was 0, and then suddenly you saw the timing residual. Let's see, this is blue shifting. The arrival times the pulses got closer together. That's blue shifting. Then some years later, they got further apart. That's red shifting, and so on. Suppose you saw that pattern. What could we conclude about the gravitational waves? This is a question for you, the audience.
They exist.
Very good. Yes. Anything more? What's the amplitude? Within a factor of 2. I only care about orders of magnitude. You can read it off the plot, at least if your eyes are good enough. Yeah, that's right. Yeah, so this is an amplitude. So this is a gravitational wave with dimensionless amplitude or strain h of about 10 to the minus 15, because the largest redshifts here are sort of plus or minus 10 to the minus 15. What else can you tell me about this wave? Which is? I can't remember anymore. I made this plot a long time ago. Let's see. From here to here, I think 5 years. Yeah, but the writing's too small. Yeah. So this is a gravitational wave with which goes through 1, 2, looks like 3 cycles. Frequency 1 over 5 years. Amplitude 10 to the minus 15. Okay. Question B. Suppose that you saw this response from one pulsar and that response from a different pulsar. Could I conclude something about the location of the source? Yeah, that's right. Say it again.
Closer to the first one?
Yep, exactly, because you saw the antenna pattern, so it's more likely that the source is, that's the larger amplitude one. So it's more likely that the source is in this direction, okay, but not guaranteed, right? Because you might be near the zero of the antenna pattern, so now we come to the problem of inference and so on. Okay, yeah.
So here the gravitational wave somehow zeroizes. So that should I conclude that it's coming either from the Earth term or the pulsar term, but not both?
No, you can't conclude that. You don't know if you're seeing the Earth term or the pulsar term. You're quite correct that your expectation now is, look at the range that this goes through. Okay, this can go anywhere between sort of 0 and L, roughly speaking. So what you can conclude is that either a few thousand years ago or in a few thousand years, you kind of expect to see another copy of that come through.
Well, if I see it also the other one, then suddenly there's no question.
Well, absolutely. Good point. You must be seeing the Earth term here because it's the same for both of them. Thank you. Yeah, better answer. Okay. All right, any other questions about this? So that's the general idea. All right, so now here's the point with pulsar timing arrays is that we unfortunately are not in this happy spherical horse situation where there's perfect data and no noise. Unfortunately, it's quite the opposite. If you look at the arrival times, the redshifts from the pulsars, they're typically noise dominated. The signal is sufficiently weak that you can't see it like that. So what you do instead is you correlate the data from multiple pulsars. And I think I got a slide or two to illustrate that. Maybe I'll just stick with this one, it's good enough. So the idea is that the Earth term, remember that was this term here, is the same among all pulsars. That just depends upon the gravitational wave strain amplitude at the Earth at time t. So that affects the arrival times from all of these pulsars the same way. So the basic idea of pulsar timing arrays is you look for that common signal. And the pulsar terms you're going to see are going to be decorrelated, at least provide the coherence length of the gravitational waves is shorter than thousands of years, which is the distance between pulsars. Okay. All right, so what that means is that unfortunately, we can't just take this nice formula. HA of F and omega, that is a function that has definite values in our universe. We just don't know what they are. But that function is not something which is, undefined or vague in any way. It's just that we don't know what the right function is. If we did, we could plug it into the formulas and calculate away what every pulsar would do. So a lot of what we're going to be doing is based on our ignorance, the fact that we don't know what that H is. And so what we're going to be doing is trying to understand what our expectations would be in possible realistic models of the universe. And so one way to do that is by constructing ensembles. And I want to spend a minute just to give you some insight into my way of thinking about ensembles. And we've already been through this once, but I'll just... So the basic idea of ensembles is this. An ensemble is something you construct in your head. So our universe is not an ensemble. Our universe, in this case, has one particular HA of F omega. We just don't know what it is, but that is a definite function, just not something we have access to. So ensembles are ways for us to create fictional model universes. The ensembles only exist in our head. They're not out there. They're our internal constructs, and we can make them any way we want. So here's an example for you. So here's universe number 1. Here's universe number 2. Here's universe number n. These are models in my head. And I want you to imagine that each of these universes contains a single complex number of modulus 1. That's it. That's all that exists in these universes. So each universe contains a number z of the form e to the I phi, where phi is an angle between 0 and 2 pi. So for example, in this universe, z is equal to 1. In this universe, it's equal to I. In this universe, it's the square root of 2 over 2 plus root 2 over 2I. Okay? There's just some large number of universes. If you happen to live in one of those, the value of z in that box, that's ours. But suppose you don't know what that is and you want to understand the effects of things. So you make up this ensemble, and you're going to define the ensemble average of some function of z, whatever it happens to be just 1 over n times the sum. And now we're going to evaluate the function in every one of these different universes. So that's the definition of an ensemble average. You build the ensemble in your head. You imagine each universe has this different state. Then you compute the function and you average it. So let's do some examples. The simplest function of all, the function f of z that simply ignores z and always returns 1. What's the expected value of that, the ensemble average of that function? Go ahead.
1.
It's 1, right? Because every term in this sum is 1. You add it up n times, you get n. Divide by n, you get 1. Okay, so ensemble average of f in this case, ensemble average of 1 is just 1. Okay, let's have a bit more fun. Suppose the function just returns the value of z. What's the ensemble average of z? Remember, I've made a large number of these universes, and I've just picked this phase at random uniformly between 0 and 2 pi. Oh, it's interesting. I heard 2 different answers. I heard pi and I heard 0. I like 0. What's the argument? How come?
Well, they're all different angles, so you
Agreed.
have a symmetry.
There you go. There's a symmetry. For every universe that happens to contain, so if you want to think about this geometrically, that complex number lies on a unit radius circle. There's imaginary z, there's real z. And for every universe that happens to contain, let's say, I, that universe, somewhere in this ensemble there's another one that contains minus I. And so we add them up, and they average to 0. So look at that interesting thing. The ensemble average is 0. Is there any universe in my ensemble that contains z equals 0? There isn't. Because every universe, the modulus of z is 1. So the ensemble average here actually does not reflect any single one of those universes. There is no universe that contains that. Let's play a few more games with this just to get the idea. What about the ensemble average of z squared? Whoever, by the way, you correctly answered the last question, so you can't answer this one. What's the ensemble average of z squared? Okay, I heard 1. Careful, I didn't say the modulus of z squared. So I'm going to write down what you just told me because it's correct, although it doesn't answer my question. You just told me that the ensemble average of z times its complex conjugate is 1. That's correct. But that's the modulus of z squared, modulus squared. I mean here the complex number squared. It's 0. How come? Why? Same argument. Exactly. I mean, now we wrap around the circle twice. It's e to the 2I phi, but for each point on one side, there's going to be another universe with the point on the other side. What about the expected value of z to the n? As long as n's not equal to 0. That's right. It's also 0. That's, n not equal to 0. Okay, what about expected value of z star? Same thing, it's e to the minus I phi, so the same symmetry argument applies. What about expected value of z to the n, z star to the m? It's only 1 if n equals m. So what's the general answer? That's, you got to handle the n equals m case also. You're drawing it correctly in the air. Can you just tell me? Thank you. It's a Kronecker delta and m. As long as n is equal to m, we get 1, because, of course, e to the I n phi times e to the minus I m phi is e to the I n minus m phi. So, so in this universe, in this ensemble, for example, if you give me any function f of z and z star, how do I evaluate that? Well, I could write that, for example, as a double sum on n and m of a n m z to the n z star to the m, at least for some class of functions. I can't call them analytic because they couldn't depend both on z and z star. But anyway, for some set of functions like that, if I wanted to evaluate the expected value of this, you can see from this formula, I just end up summing the diagonal values of these coefficients. And that would be the answer. So this is how I like to think about ensembles. I like to think that it represents some set of imaginary universes that we've constructed because we think it's representative of whatever physical processes are making something that we want to understand. And they're used in statistical mechanics somewhat differently. You might look at the light coming from that bulb there and say that there's a very large number of atoms in there which are emitting, and somehow represent them by an ensemble like this. But that's not really what we need for sort of cosmology, gravitational waves, and so on. Okay. So we're going to be constructing ensembles of different h's. And I'm going to shove this up to the top and maybe erase it later. Now, how are we going to do that? So I have to confess here, I'm going slower than I thought. I wanted to construct an ensemble of gravitational wave sources using what are called random phases. It's actually exactly the same idea as this. Basically, we put point sources of gravitational waves in space. We assign them a frequency, and we give them a random phase, meaning, what's the relative amplitudes of the sine and cosine components, or you have e to the I times some phase. And then what we say is that each different universe has the sources in exactly the same place in space. They have exactly the same distance from the Earth. The only thing that makes one universe in our ensemble different from the next is that the phases that we assign to these gravitational wave sources are going to be different in each one. And guess what? Each one gets a phase assigned just like this at random, but independently for each of the different sources. That sort of model, a set of random phases, is actually probably quite a realistic description of the kinds of radiating sources, supermassive black hole binaries, that kind of stuff. Unfortunately, it's something which isn't very much used in the community, and I realize I don't have time to do all the ensembles that I wanted to. I wanted to show you an ensemble of random phases, but I just don't think I have the time, and I decided it would be better to show you the ensemble that's most widely used, which is, you can guess it, the Gaussian ensemble, the one that you've been seeing from other speakers here. So I'm going to show you how pulsar timing arrays work for Gaussian ensembles. And I'm also going to try and connect this a bit to the things that the other speakers have been talking about. By the way, one of the reasons that Gaussian ensembles are so commonplace and so popular is because of the central limit theorem. The central limit theorem says that if you have a large number of random variables, for example, the amplitudes of different gravitational wave sources, and you add them together, because of course our detection here is linear in H, so if you have many different sources, their H's all add together, then the resulting distribution in the limit as you take a large number of terms approaches a Gaussian. And that's a very easy theorem to prove, and if you haven't proved it at some point, you should. It's just a few lines. Come and ask me at coffee if you want to see how. This actually applies very well, for example, for noise processes, because in electronics, for example, noise processes arise because there's a lot of electrons jiggling around in semiconductors and resistors and things, and their effects add up. But for example, if you want to model gravitational wave sources for PTAs, we've got one source that's perhaps 100 megaparsecs away. We've got another one that's 300 megaparsecs away. The Gaussian limit would be the one where there's, the first source is, 1 meter from me, and the next one is 2 meters from me. So the Gaussian approximation probably applies quite well to cosmological sources. These are at cosmological distances, and there's extremely large numbers. Probably does not apply to astrophysical type sources, especially when there's, let's say they're widely separated. So, okay, mea culpa, I wanted to show you not a Gaussian ensemble, but I'm going to do this one instead. So one way of defining this is in terms of the probability distribution function. This is how Barak did it yesterday. You say that the probability of x1, x2 up to xn is a normalization factor. It's 1 over the square root of the determinant of 2 pi times the covariance matrix. And then there's an exponential factor, which is e to the minus 1/2. There's the vector x minus its mean transpose the inverse of the covariance matrix, and then x minus mu again. And that's the probability distribution function. People would write that by saying that x is an element of a normal distribution with mean mu and covariance c. So that is the complete definition of a multivariate Gaussian distribution. Hopefully I got my factors right. There's another way of doing it. And actually, for what I'm going to do, that's preferable. And that's the following. You say that the distribution, a Gaussian, can be completely defined by the following 3 properties. First, you tell me what the mean is. By the way, for this distribution, that mean value is called mu. Secondly, you tell me what the covariance is. That's the, in this case, it's c, and maybe I'll write it as the expected value of x times x transpose minus the expected value of x times x transpose, like that. Okay. But then there's a third property. And very often when people write down Gaussians, they write down these 2 things, and then they sort of assume that you know what the third property is that defines the Gaussian. But it's actually often left out. And that is called Isserlis's theorem. Isserlis was a Russian mathematician born in the 1860s who emigrated to London. And he was actually a student of Niemann, the same Niemann that you heard about in the Niemann-Pearson lemma. He also, I think, worked a lot with Fisher. He died, I believe, in the 1960s. Unfortunately, most people in this audience, if you learned Isserlis's theorem at all, it was called Wick's theorem. Wick was an Italian physicist. Wick's theorem dates the 1950s. Actually, Isserlis published the same thing in the early 1920s in a journal called Biometrica. So it should be called Isserlis's theorem. And Isserlis's theorem says the following. It says if you have a Gaussian, and you want to know what the expected value, so we know how to calculate expected values from that probability distribution. In principle, we could do it like this. We could say if we want to know what the expected value of x1 times x2 times x3 is, just do the integral over all your x's of x1, x2, x3 times this probability distribution. That's kind of the definition of the expected value. But Isserlis's theorem says that for a Gaussian, you can write that always in terms of the first and the second moments, mu and c. And the rule is the following. You just write down all possible combinations that involve only first and second moments. So I'll just do it for this case, x1, x2, x3, plus x2, x1, x3, plus x3, x1, x2, plus, that's it. I stop there. Okay, I just wrote down all combinations that sort of match. And this applies to higher orders as well, so if you wanted to know what the expected value of some product of x's with 5 of them, you just write down all the possible terms. Yeah? Oh gosh, thank you. Yes, fantastic. Any other mistakes of note? Okay, thank you very much. So this is another way to define a Gaussian. You say that it has a given mean, it has a given covariance, second moment, and then all higher moments can be computed in that way, and that's equivalent. It's actually more useful for the kind of calculations I'm going to be doing, and especially, for example, for the kinds of processes that we're interested in are zero mean ones. And for the zero mean ones, this gets even simpler. For example, the expected value of x1, x2, x3, x4 for a zero mean process would just have the terms x1, x2, x3, x4 plus x1, x3, x2, x4 plus, I'm running out of space, x1, x4, x2, x3. Even if you can't read that, I hope you got the idea. All right. So anyway, that's what we're going to use for our Gaussian distributions. And just a comment about PTAs. What Barak talked about yesterday was optimal tests for the following thing. He was comparing two hypotheses. In one hypothesis, hypothesis 0, your data is drawn from a normal distribution with mean 0 and a covariance matrix that describes the noise C. And then the signal hypothesis, at least in the very simplest case, where there's just one template, was that the data was drawn from a normal distribution whose mean was given by the template, but with the same covariance matrix. And so the analysis problem was, how do we make a test to distinguish between these? For PTAs, actually kind of interesting, for PTAs, the null hypothesis, the equivalent of this one, is actually that the data is drawn from a normal distribution with zero mean and a covariance matrix C, which is roughly speaking diagonal. That is, the data from this pulsar and the data from that pulsar are not correlated with each other. So this is, maybe I'll write diagonal. There's no cross-correlation terms, whereas the signal hypothesis H1 is that the data is drawn from a normal distribution whose mean is still 0. That's the difference. But whose covariance matrix is, I'll just write non-diagonal. And that's because it reflects the correlations caused by the gravitational waves between the different pulsars. And so that's today's task. I'm going to be calculating that, at least getting started on that. Okay. Good. So how do we do our definition of our Gaussian ensemble? So I'm now going to imagine that I've got my very large number of different universes, and in each of them, I'm going to assign a different function, h of f and omega. And each of those satisfies my requirement that, h of, I guess HA, pardon me, I need two functions, one for each polarization. And I'm going to assign those, so that HA of f and omega is equal to HA star of minus f and omega. So they'll satisfy the requirements that real, but every single universe is going to have a different one of those. And by the way, one of the beautiful things about the Gaussian distribution is you notice that it's never zero. The exponential is never zero. So there is going to be our universe in there, guaranteed, somewhere. So the h of f and omega that's appropriate for our universe does sit somewhere in that ensemble. And the way we're going to make that ensemble is the following. Now, I have to tell you what the mean value is. So I have to tell you what the expected value of HA of f and omega is across that set of different universes. Yeah.
What is exactly the data a lot of things from different pulsars? What's the data that you claim is that? It's normal, I don't know.
It's the redshifts z, so like these plots, from each of the different pulsars as a function of time. So typically what happens is the pulsars get observed maybe once a week or once every month over a period of many years. And so what you've got is you've got a time series from every single pulsar that stretches over that. Now, I'm giving the spherical horse version, okay? There's complications, there's missing data, it's not sampled evenly, and so on. But that's it.
There's an even bigger complication. We are not observing z, we are observing the phase of the pulsar, which is not exactly z.
Yeah, yeah. All right. So how am I going to construct my ensemble? So first of all, so again, it's going to be a Gaussian ensemble, and that's completely defined by telling you the mean, the covariance, and saying it satisfies Isserlis's theorem. That's enough. So the mean is going to be 0. The covariance, that's the same as the correlation, is going to be defined by a formula that's very simple, similar to something that Teja already wrote down. So I'm just going to write it, and then I'm going to try and give it some justification. So this is now the covariance between the amplitude at frequency f and direction omega and f prime at omega prime. So there's going to be a spectral function h of f. Teja, this is two-sided. That's why I don't have a factor of a half. And there's going to be a delta function of f minus f prime. The justification for that being that we want a stationary process. If we're modeling gravitational wave backgrounds, human lifetimes are, decades, hundreds of years, whereas the processes that produce these things have been going on for millions or longer of years. And so at least, we expect our snapshot of this is going to be stationary statistically. And then there's a delta function in the polarization A and A prime. That's just the statement that we expect no correlation between the two different polarizations. They're independent of each other. And finally, there's a two-dimensional delta function of the direction omega and omega prime. And there, if you want to think about it in terms of individual sources, it's basically telling you that the source at one sky position and a different one are independent of each other. As I said, this is actually, in my opinion, not such a good approximation or model to use for realistic PTA sources, but it is the standard one of the literature, so I don't feel completely guilty about teaching you something which is probably wrong. And then, of course, this was statement 1, that's statement 2. Statement 3, I'm just going to say Isserlis. That's how you get the higher moments. So based on that, we're going to do a calculation, which is what's the correlation between the redshift of two different pulsars in this approximation. And I'm looking at the clock. Do I have to half past or till 1:45? quarter to. I've got half an hour. All right, I'm going to do two calculations. I'm going to do a warm-up one, and then I'm going to do the pulsar correlation thing. So, yeah. All right. Actually, I'm going to try and do three calculations. Let's see how far I go. All of these are meant to, you see, the redshift one, when I write it down, it's going to fill one of these boards, and it's going to give everybody here sort of an unpleasant feeling in their stomach. So I want to give you an easier version first, so that when we get to that, you actually think, oh, this isn't so bad. So let's start off with the following. Let's take our expression for the gravitational wave strain, HAB of t and x. I'll remind you what that looked like. That's the sum over polarizations, integral over frequency, integral over directions. There is this exponential factor for the plane waves. There is the amplitude, HA, F and omega, and finally polarization tensor, EA, AB of omega. Okay. Did I leave anything out? Yes? No? I think I didn't. All right. So remember now, the idea is that in every universe, we've got a different one of these HA of F and omegas. And so, for example, the expected value of the strain we go into each universe, we calculate this, and then we add them all up and divide by n. So everything in this integral here is completely deterministic. For example, the value of t and x at any given point we pick the same point in every universe. The only thing that changes from one universe to the next is this h here. And so I'm perfectly justified in moving these expectation values around that h. And as I wrote down somewhere, the expected value of that is 0. So we conclude immediately the expected value of HAB is 0. That was easy. What about the strain squared? Let's do that. All right. I'm going to start here and move down onto this next board. Let's see if that works. So suppose that we take the gravitational wave strain at point t, time t in position x. We contract that with the same thing. And we ask, what's the expected value of that? So that's a scalar quantity. It's sort of the strain squared, the sum of all the different components. Well, we write down this thing twice. Once with the sum over a, integral over f, and integral over omega. Another time with the sum over another index, a prime, f prime, omega prime. We then take these expectation value symbols and we move them inwards until the only thing that's left inside is the HA of f omega and the HA prime of f prime omega prime. Let's do that. By the way, okay, I can't help saying, this is clever side remarks. Hopefully Javier won't catch me on this clever side remark. I think this is correct. You might wonder, by the way, what about the expected value of HA of f omega, HA prime of f omega prime? How do I calculate that? Anybody tell me how I do that? Given the information that's there in 1, 2, and 3. I snuck this in before. Remember, in every single universe, right, this quantity is real, and that means that HA of minus f omega is the complex conjugate. So if you want to get this quantity, just change the sign of f in here. So that becomes h of f delta of f plus f prime. It's not 0, but you can compute it. Okay, one other interesting comment. No, I better not do that. I'm going to run out of time. All right, so let's go ahead and do a calculation here. Now, because this quantity is real, the HA of the second h here, I can complex conjugate it without changing the result. So I'm going to do that as I do the calculation, just because it makes it easier. It means that I get something that contains one HA and one HA star. And so I don't have to change signs of f. But I could actually put everything in and go ahead and do the calculation as is, and I'd get the same result. So here we go. We're going to have a sum over a sum over a prime. There's going to be an integral over f. There's going to be an integral over f prime. There's going to be an integral over omega, and another one over omega prime. Then there's going to be an exponential. It's going to be 2 pi I f t minus omega dot x. And then there's going to be a minus f prime t minus omega prime dot x prime. Remember, that change of sign here is because I put a complex conjugate on that second one, since it doesn't change anything. Then we're going to have a polarization tensor, EAB of omega, A, contracted with a polarization tensor EA prime, AB of omega prime. And yeah.
Is the second HAB, there's an x prime, or is it just x?
It's just x. Thank you so much. We could do this, by the way, with t prime and x prime if we wished. The calculation goes ahead, and you'd be very happy to see that you get sort of appropriate Fourier transforms in there, but I'm trying to do the simple case here. Okay, and finally, last but not least, we have an HA of f omega and an HA prime star of f prime and omega prime. Okay. So I hope I got that right, because otherwise I'll have to pull the board down and fix it. Okay. Before I go on, any comments? Are there any other mistakes here that I've missed? Can I get a thumbs up from somebody who's actually looked carefully at what I wrote? Thank you. Okay. All right. But now, our life gets simpler. Because this expected value here, as you can see, it gives us a delta function in polarizations, it gives us a delta function in frequencies, and it gives us a delta function in the integral over the sphere. So instead of having double sums, double integrals of everything, it immediately reduces to 1. So it means that the expected value of the squared strain now becomes a single sum over a single integral over f, and a single integral over directions. Because f is equal to f prime, and because omega is equal to omega prime, the argument of the exponential is now 0. The EAB becomes that. We get a spectral function h of f. I think I got it all. Okay? Good. All right. Well, this quantity is easy to calculate. You remember that E was either m hat minus n hat. That was the plus one. And if you dotted that into the same thing, m hat minus n hat, you get a 1 from this dot product and another 1 from that. So you get 2. Same thing for the cross polarization tensor. That was m hat n hat plus n hat m hat. Dot that into itself, and you also get 2. So the only thing here that depends upon the polarization A is this. And I just told you that the plus gives you 2, the cross gives you 2, so the sum gives you 4. So that's the 4 times the integral d omega, integral df, h of f. So 16 pi integral dh, h of f df. And by the way, this shouldn't be so surprising because this h of f is like a power spectrum. It's telling you how much energy you've got in your gravitational wave background at frequency f. And this is just roughly speaking the total power. It's actually h is the spectrum of the strain rather than the spectrum of power. Okay. All right, so that was easy calculation number 1. Let me stop and ask, if there's any questions now, please ask them, because this will look a little bit messier in a minute.
Is it full contraction over the polarization indices and the tensor indices, so we lose information?
Good question, yeah. So I realized something. I've been using the Einstein summation convention here sort of from beginning without ever even saying that I was doing it. So indeed, the indices here, A and B, are contracted from 1 to 3. Let me just do one explicitly. So for example, what I mean by E plus AB is I mean M hat A, M hat B, minus N hat A, N hat B, where M and N are those vectors that I defined in sort of first lecture. Who asked me the question? Was it? Okay. So far, so good? Okay. So now, if we form E plus AB, E plus AB, what I mean by that is I mean take M hat A, M hat B, minus N hat A, N hat B, and dot it into itself. Like that. So far, so good? Okay. Now look at the dot products, right? This is just M hat dot into M hat, which is 1. And that's M hat dot into M hat, which is also 1. So we get a 1 from there. This cross term is N hat dot into M hat, but N hat and M hat are perpendicular, so that gives 0. This term dot into that one is, again, N hat dot N hat squared, also 1. So we just get 1 plus 1 equals 2. Okay, and the same calculation holds for the cross. You can work it out. Yeah.
I was trying to ask, like, if we don't do that, so it gives us
Oh,
angular dependence, and could it be, for example, used to verify the tensor later?
You got to be very careful here, because what you'd like to do, what you're asking me to do is say, do this computation. That's what you're asking. But that doesn't work, because think, plus is defined for a particular gravitational wave propagation direction. Saying H plus doesn't have a particular meaning. You could do this. You could say, oh, I have a detector which has arms x hat and y hat. And so I want you to look at this quantity, x hat A, x hat B, minus y hat A, y hat B. That's the response of one detector, and I want to know what's the expected value of that times the corresponding quantity, CD, maybe for some different detector, Z hat A, Z hat B, minus W hat A, W hat B. That's a question you can ask and you can calculate. And in fact, this is exactly what's done in calculating overlap reduction functions for ground-based detectors. Because you have one detector in one location with a particular set of arms, another detector in another place with another set of arms. And all of the machinery here for doing these calculations can be applied. So you do the calculations exactly the same way. You satisfied with that? Okay. Are there any other questions? Okay. So I'm going to erase this, I think, because I want to do the other calculation on the side. So I'm going to erase my scribbles here, some of this. Okay. So now here's a more interesting quantity. And yeah,
Maybe also deleted pluses, remove the pluses from the HAD.
thank you. Yes. Good. All right. Next calculation is actually physically quite interesting because I got to check my factors right now. That's right. This is effectively the formula that Matthias wrote down in his first lecture. H is like a potential, like an electromagnetic potential. You take a derivative of it and you get a field, like the electric field. Square that and you get an energy density. So the energy density in gravitational waves is related to the time derivative of the potential in this way. And you got to be a little bit careful because you have to average that over a volume which is large enough to contain, at least a few wavelengths, and over a period of time which is large enough to contain a few cycles. Otherwise, the meaning of energy in GR is a bit problematic. So let's use this to calculate what's the expected energy density associated with our Gaussian ensemble. Now, the beauty of this is I don't have to do any more work. Because if you look at the calculation I did, suppose that before we take the expected value, we take a time derivative of h. So when we take a time derivative, all that happens is that exponential, e to the 2 pi if t, you bring down a factor of 2 pi if. We do that, we bring down a 2 pi if here, and we take down the derivative of that. And here we bring down an e to the minus 2 pi if prime. Then we set f equals f prime with the delta function. And so we can just write down what the answer is. Same thing I've got here. Then there's going to be a factor of c squared over 32 pi g. And then there's going to be the exact same integral I have there, except with the factor of 2 pi I times 2 pi minus I. I somehow feel like I'm missing factors, but I guess that's probably right. Thank you. Good. Yeah, that's right. Okay. All right, so we've got 64 pi cubed on the top and 32 pi on the bottom. That's 2 pi squared. C squared. There's a c squared on the top, a g on the bottom, and we've got an integral of h of f squared df. In Teja, that is a two-sided power spectrum, so the integral goes from minus infinity to infinity. Okay, so if we want to, just for the heck of it, we can now compute, for example, what's the spectral function omega GW of f, which I introduced in the very first lecture. So let's do that for this. I am now going to violate all the laws of good Blackboard technique and work to the left here. Apologies. So what was that definition? I defined a dimensionless spectral function omega GW of f it was F divided by the critical energy density times d rho in gravitational waves, energy density in a frequency interval df, df. And the critical energy density, what was that? Critical energy density was defined by, let's see, Hubble constant h squared is 8 pi g rho over 3c squared. So the critical energy density, I'm just going to write it down. Okay. So what's that? That's F. The critical energy density is going to be 3c squared, h squared, but I need the inverse of that. So I guess that will be, 1 over that is, it's going to be 8 pi g over 3 c squared h0 squared. So I've got my factor of F. I've got my factor of 1 over rho critical. And finally, I need to know what's the energy density here between frequency F and df. That's exactly this integrand with a factor of 2, because we want one-sided and not two-sided, based on our physical definition. And so I'll just read it off here. So that's going to give me a 2 pi squared c squared over g times a factor of 2 to make things one-sided times h of f squared. Okay, I hope I got all the factors copied correctly. You nodded yes? It's okay? Good. All right. Great. So now we can have a little orgy of crossing out factors. The g's go, the c's go, and we get, at the end of the day, omega GW of f equals, let's see, there's an 8, 16, 32 thirds. We've got a pi cubed upstairs. There's an h0 squared down, so let's just say h0 to the minus 2, and then f cubed h of f. I'm going to glance at my notes just to see if that bears any resemblance to what I have here. Almost, except I made a mistake in my notes. I left out the h0 squared. So I think I believe that. Okay, so this shows you the way that the spectral function h of f in this covariance written over there is related to energy density. So this is a physical quantity, just relating it to h. Okay, anybody spot any mistakes in this, or is this okay? I'm just looking for missing factors of 3 and c and things like that. Okay, I don't see anybody raising their hand. All right, so now let's get to the finale here. I want to calculate what the correlation is between the redshifts of two different pulsars. That was kind of the point of all of this. Using this Gaussian ensemble model, which, as I said, I think doesn't actually really apply so well, but it is standard in the literature, so that's some reason for doing it here. And there's one interesting subtle point that comes up, which I'm looking forward to talking about. And hopefully it's something which people here will have a good understanding of afterwards. I'm just trying to think how to structure the boards here so I leave some useful stuff for you. I think what I'm going to do is I'm going to pull down my ensemble averaging and leave up the other stuff. Let's do that. So we're going to leave that. We're going to leave these two sample calculations. And then I'm going to pull down this one. All right. So we're going to ask, what's the expected value of the product? Now I'm going to do something that's really bad style. I'm going to change my notation. So until now, I've been using A and B as indices, for example, for vector and tensor components. I use A and B because of the first letters in the alphabet. And I don't write Greek letters very well. Now I'm going to use them for a different purpose. I'm going to use them to denote pulsars. So that's going to be pulsar A, and that's going to be pulsar B. So I'm going to take my formula for Z. I'm going to put an A on it. Tau is still going to be the arrival time. Actually, I guess I could change that to T. I don't need a T for anything else, so let's make that a T. And I'm just going to copy again my formula here, but just pointing out the places where this depends upon the pulsar, because that's actually important. So we've got our sum over polarizations A. We've got our integral over frequency. We've got our integral over directions. There's the amplitude, frequency F, and direction omega. There's the antenna pattern function F. So I'm going to write it like this. I'm going to write F sub A. There's omega. That's the gravitational wave direction. But then there's, of course, the pulsar direction. And that pulsar direction depends upon the pulsar. So I'm going to put an A there. That is not the same A I've been using previously. Previously, when I wrote P hat A was X, Y, and Z, or 1, 2, and 3. It meant the component. It doesn't mean that anymore. It means which direction vector to which pulsar is that. Okay? Okay. I squared is -1. Wrong symbol. Okay. Good. Then we've got our e to the 2 pi I f tau. And finally, we've got the difference between the Earth term and the pulsar term. Now, remember there's an L here. That's the distance to the pulsar. So that's going to become an LA. Depends upon the distance to this particular pulsar. And then there's a 1 plus omega hat dot PA. And again, that index there is just which pulsar.
Is it T and not tau now?
It is. Thank you. It's funny. When I started teaching, I used to be sort of nervous when I was lecturing. And then I got to know my students in my classes, and I'd be sort of nervous for the first couple of lectures, and then I'd relax. Because they realized I was human and made mistakes, and I realized that they were human and sometimes asked things that might not have been the best questions. Anyway, thank you for fixing these things. All right, so what we're going to calculate now is the expected value of ZA of t times ZB of t. By the way, we could do this for t and t prime, also interesting, but I want to keep it as simple as possible. So in the spirit of the first calculation, we're going to have sums over a and a prime, integrals df and df prime. There's going to be integrals d omega and d omega prime. Let's just go through our factors here. Oh, by the way, same thing as before. Z here is real. And so I'm allowed to take the complex conjugate without changing anything, and I will be doing that in this calculation. So the first thing I'm putting in is going to be as written above. The second one is going to be the complex conjugate, so I'm going to change the sign here. So we're going to have an e to the 2 pi I f minus f prime times t. There's going to be a geometrical response for pulsar A in direction omega and same quantity in direction omega prime for pulsar B. And then, and this turns out to be interesting, there's going to be the difference between the Earth and pulsar terms. For the first and for the second pulsar. And you notice that you'll notice that in these differences, there's two different lengths here that occur, length to pulsar 1 and length to pulsar 2. And finally, last but not least, the expected value, oh, this is terrible notation, I'm just going to write it down here, times the expected value of HA of F omega, HA prime of F prime, omega prime, complex conjugate. Ooh, I made a mistake. Anybody spot it? Yes. I forgot to complex conjugate. Remember, I'm complex conjugating my second quantity. That's why there's a minus sign here, and that should be a plus sign there. That's going to turn out to be important later. Okay, any other mistakes of note? All right. So, same thing that we did before also applies here. We can simplify in the same way that we did here, because remember what happened here is that this expectation value just gave us two delta functions. So it reduced the number of sums, the number of integrals over frequency and direction. So same thing happens here. We get delta functions here that chop everything down. So it immediately gets simpler. I think I'll be able to write it on one line now. We're going to get a sum over A, an integral df, and an integral d omega. Since f is equal to f prime, t disappears. So we're going to get an fa of omega hat p hat a. Then there's going to be another f, also polarization A, of omega hat p hat b. So there's our two pulsar directions appearing. We're going to get a spectral function h of f. And finally, last but not least, we're going to get the product of the difference between the Earth and the pulsar terms. And that I'm going to write out in full because it's going to turn out that that's got some very interesting features. Yeah.
So when we write out the expectation value of ZA of t and ZB of t, are we assuming that pulsars A and B have the same arrival times?
The way to think about this ZA of t is kind of related to the plot that I have here. That's a time series, right? It's defined at all times. It's how much earlier or later does the pulse arrive than its expectation from a regular clock, okay? And again, you have to imagine that you have many different universes. In each one, you're given h of f and omega. That means you can calculate everything. You can tell me exactly what z of t is going to be for every single one of those pulsars. And so now, you know, in each universe, you've got this time series. First universe, second. You pick a time t. You look at what the product of the redshifts is in universe number 1, then you look at that same product in universe number 2, and you average. Does that answer your question?
I think so, yeah.
Okay. Any other questions? You notice this quantity is independent of time, right? The time dropped out. That's because it's a stationary process. Okay. So let's look at this and see what's going on here. First of all, these F's here, these don't depend upon frequency. They only depend upon polarization. So I can move this sum over the A's, kind of, it just attaches to these F's. What about the frequency dependence? Well, there's frequency dependence here in the H of F, and then in these two factors, the differences between the Earth and the pulsar terms. Now, the product of the 1 and the 1, that's frequency independent. That's the correlation between the two Earth terms. If all we had was those two terms, our life would get very easy, right? Because all we'd have here would be an integral df of H of F. That pulls out. And then we have the sum over A of FA times FA averaged over omega. That, by the way, is the Hellings and Downs curve. But there's three other annoying terms here. And let's look at what those are. For example, look at the product of the pulsar term from the first pulsar times the Earth term from the second one. Now, imagine what this is like. You should think of H of F here as some, let's say, rather slowly varying function of F. But look at what happens here as a function of F. This quantity here, LA times 1 plus omega hat dot PA, for most values of omega hat, this quantity is very rapidly varying, either as you vary F or as you vary omega. So we've got slowly varying functions of omega in these, but very rapidly varying functions of omega in the product of this pulsar term and the exponential. The pulsar term and this Earth term, or in that pulsar term and that Earth term. So we're going to throw those terms away. We're going to say that's a rapidly oscillating function that gets averaged away. Now, what about the product of the two pulsar terms here? The same argument applies to those. There's a very rapidly oscillating function of omega hat that averages away, except for one case of interest. When would that not be true? When would those last two terms, the product of this term with that term, so I heard the right answer. When they're the same pulsar. Because, of course, if A equals B, if we've got the same pulsar, then the product of this term with this term is 1. That doesn't average away. So what we've got here is the following. There's an integral df of H of F. Then there's an integral d omega times the sum over polarizations of FA of omega p hat A with FA of omega p hat B. I'm going to put square brackets around that just to set it off for you mentally. And finally, we're going to replace the four terms, the products of this with this, with 1 plus delta AB. The delta AB reflects the fact that the two pulsar terms are correlated exactly in the case where it's the same pulsar, because then you get the autocorrelation of the Earth term and the perfectly equal autocorrelation of the pulsar term. So this doubles the correlation of a pulsar with itself. So what's basically going on here is that this calculation is assuming that the two pulsars are far away from each other and far away from Earth on the scale of the gravitational wavelength of interest. So, you know, if a couple pulsars, if one of them is, 3,000 years from the Earth and the other one is 5,000 years from the Earth, they're very likely to be less than 10 years apart from one another. So that's So strictly speaking, this 1 plus delta AB only holds under that assumption, holds under the assumption that the pulsars are far away from each other compared to the coherence length of the radiation, and that they're also far from the Earth. Okay. All right, so I'm actually able to finish the lecture now. I just want to write down one last thing. So what have we got here? We've been looking at the correlation between pulsars A and B. And what we've found is this is given by some integral over frequency, which we now know, by the way, is just related to the mean squared strain. That's like the average value of h squared. So this is the average value of h squared. Then we've got something which doubles if the pulsars are the same. So it introduces a factor of 2 for one special case. And finally, we have this interesting integral. I'm going to call that integral mu. That means mean. U means unpolarized. And you notice that this integral depends upon the direction to two pulsars, p hat A and p hat B. It might not surprise you to learn that this integral, once you've integrated over all the directions on the sphere, actually only depends upon the angles between the two pulsars. And so I'm going to call that gamma. And by convention, this goes back to Hellings and Downs in the 1980s. They defined this as an average over the sphere. So they threw in a factor of 4 pi. Whoops, I'll do it like this. Omega p hat A, f A, omega p hat B. And here gamma is the angle p hat A to p hat B, meaning that the cosine of gamma is p hat A dotted into p hat B. Okay. So this is called the Hellings and Downs curve, or the Hellings and Downs correlation. And it gives rise, this is the topic for the next lecture. I'm sorry I've run over time here. This gives rise to a correlation between the redshifts, or timing residuals, from different pulsars. And as I explained earlier, what pulsar timing arrays are trying to do is look, their null hypothesis is that there is no correlation between different pulsars. And their signal hypothesis is that there's a correlation described in this way. And so that's the signal analysis problem. I'll talk about that more in the next lecture. If I made any mistakes, please point them out now, just so that this isn't wrong in people's notes. Okay, thank you all.